there's a lot of slides, like 170 slides, but we're not going to go through some. I'm going to jump, sometimes I'm going to jump, because I need a lot of time to do all these slides. There's a lot of material. The reason is I will jump to the most important points, and then people who need to go back and get details, there are details here, and there's details in the references. I give a lot of references that you can find much more. I want to bring out some important points of how we can do what's called, what we can call scientific machine learning. Okay, machine learning, we see machine learning uses the data. The data is data. Okay? But there's no science in the data. The question is, how do we combine science with the machine learning? How do we make machine learning more scientific? Or, if you like, how can we try to ensure that the machine learning model also respects or also follows or obeys or approximates the physical models that we know exist. That assumes, of course, that you know some physical model. But very, very often, we do have a physical model. SciML models for COVID. It's just one example. Of course, we know many things. So, the question is to be thought. So, what's another program I'm not going to do? It's very, very long. I have hundreds of, literally hundreds of slides on the subject. There is the details are quite complex, but the principles are very simple. It's based on some very, very simple mathematical principles. And I believe that if you understand the principles afterwards, the details you can always learn when you need to understand it. So I'll speak about scientific machine learning. You'll see that scientific machine learning relies on what's called differential programming. So it's important to speak about differential programming. And then the differential programming is used together with neural networks. Okay, and then these neural networks can be used to solve what we call forward and inverse problems. Okay? And then there's a lot of them. There are many different types, many ways of combining physics or science with machine learning. So I'm just going to speak about number 7. Okay? We don't have time for all these. It takes a lot of time, there's many details, but if you need, you just know that I'm going to show you one possible approach of combining machine learning with physics. When I say physics, it means computational science, models, ordinary differential equations, partial whatever you want. Anything that we've done, models that we have for physics. Okay, so what is scientific machine learning? So, okay, it's a field of research where we're going to combine traditional scientific modeling with machine learning. That's the whole idea. Its aim is to develop new methods and tools to solve scientific problems in such a way that they're more accurate, efficient, generalizable, and very often we can do with machine learning things that cannot be done in a reasonable time, sometimes because of the complexity of the underlying physical phenomenon. So you see, we have data sources. Okay, the data we've got whatever, computers, rainfall, etc., wind. It's coming into this box, and in this box you see you've got a machine learning model and a physics model. And you see there's arrows. So these two guys have to speak to each other, and communicate, and collaborate with them. And then we can hopefully get machine learning models or outputs that have machine learning information and have physics information built in. That seems like very ambitious. Oh, in fact it is. But in the last 2018, the first papers on the subject came out in maybe 2018, 4, 5, 6 years ago. And the last 5 or 6 years, there's been a lot, and there still is ongoing, a lot of research work being done on this, and a lot of publications coming out, and a lot of code that's available. So there's no reason to wait you can start to use it immediately. Okay, so another way of looking at it, in fact, it's what I call the question of balance. How much should be data-driven machine learning? How much should use scientific knowledge? And the answer to that is to use what's called multi-objective optimization. This is one approach. There are other approaches, but multi-objective optimization means we can somehow have multiple, more than one objective. In the data-driven approach, what do we minimize? We want to minimize this cost function, the MSC. So if we can add something, another term to this object, it's called the objective function or the cost function, that describes or that contains the physics, then when we minimize, we will not only be solving y minus y hat, but we will also be solving that y hat is close to the physical model. So somehow we have to represent the closeness of the y hat. Not only to the observations, the measurements. Okay, you remember that with measurements, you always have measurements coming in. You want to use the measurements because you say, okay, we've been trying to solve our physical models for a long time, and we haven't really been using the measurements. Now, with a lot of measurements, can we use the measurements together with the machine learning models to improve our physical models? And not only to improve, but okay, the idea is, as you see, I have to take a test tube with data and to take a test tube with models. I have to pour them in the good proportions and hopefully I'll have a good prediction. Okay, it looks simple, but in fact, it's as simple as this, except that there are lots of details on that, and that's what makes it complicated. You could say, somebody said, scientific machine learning is model-based data-efficient machine learning. Okay, so it's machine learning which uses data but also has models inside. Okay. So why does machine learning need science? Okay, so that's a good question. Of course, there's an answer. Because black box methods cannot be trusted, right? Very often we can get an output that can be physically inconsistent. I mean, you can minimize. You see, I can minimize this thing quite easily. But it doesn't mean that the solution that the machine learning is giving me is necessarily physically consistent. So we just want to ensure that it's physically consistent. And then, we say, oh, we have some interpretability. So machine learning methods and algorithms, they can and they do very easily learn what's called spurious or local relationships that look very good on training and eventually even on test data. Okay. The problem is they do not generalize very well and they lack interpretability. So if I have a very important critical application and machine learning gave me something, the machine learning I'm going to use with neural networks is not at all interpretable. Very, very difficult to interpret because it's a huge, huge box with millions and millions of things going on and nobody can understand. If I've made a good blend, okay. So, this physics part gives me interpretability into my machine learning. That sounds great. How are you going to do it? I'll show you we can do it. It's based on optimization to a large extent. So we have to go back very quickly and look at optimization because in fact it's optimization that's going to solve the problem to a large extent. So all machine learning is based on the solution of an optimization. That's it. If you want to know mathematics, what is machine learning? It's optimization. What are you optimizing? You're minimizing a square error. It's as simple as that. And then the neural networks, give me any machine learning method, I'll show you that underneath, well, there's some that are not the same. Underneath the machine learning method, we open, it's like the car, you open up to the inside, there's an optimization problem being solved. But we know that there are many problems in CSCs, computational science and engineering, and also optimization. So, optimization has to do with optimal control, optimal design, data assimilation. Data assimilation is what's used to do numerical recognition. In those problems, we'll always speak about that. So optimization is something that is common to both. There's something to be done. So let's just look very quickly at optimization. Why? Because optimization is very central and one needs to have a good feeling of what optimization is. Why optimization is. So typically, optimization routines use what's called local information of a function and then iteratively then try to approach a local. In the very rare case, this is very accepted. In reality, function, and then we can have explicit uniqueness of a single global minimum, which is this one. But in reality, this is more reality, and this is reality in one dimension. Y is a function of a single variable. Reality doesn't mean the same thing in reality. The space of independent variables is of the dimension big N, and big N can be 100, 1,000, a million, etc. So what happens here, we don't do a good job of optimization, we get stuck in some other limit. And when we go up to higher state, this is just a 2D function. In a 2D function, you have to try to minimize this. Very, very. So it gets even worse, I say, when there's noise in the system, the optimization becomes impossible. Okay? For us, using classical optimization method. This is why I'm saying this is. I spoke about it, maybe not you, but next week. Machine learning solves this very, very complicated optimization problem. Here it is. So, you understand, in computational science, we have an interest to use machine learning because the tools that have been developed in machine learning are extremely, extremely efficient optimizers. They can optimize things that in computational science we've never succeeded in optimizing. Look at these functions. These functions are extremely, extremely difficult to optimize, to find them. This is a stupid example. This is also 2D. I mean, it's nothing. Put yourself into 20 dimensions or 30 or 1,000, you can imagine what it looks like the surface to optimize it. And if you add noise on this. So you understand, as computational scientists, we have strong interest to look at what machine learning can do and why they do it and how to. And at the same time, what I said to you, the problem with machine learning is that it's like a black box. It's not interpretable in terms of the physics. So you see why we motivated to try and find it. Okay, so very good. Differential programming. So to optimize, we use a gradient. To use a computer gradient, we need to differentiate. And so traditionally, in computational science, we use symbolic differentiation, and if you use CIMPA or Mabel, we have codes, software that differentiate. F of x equals sine of x, and it will give you that the f of x equals cosine of x. So it knows all the primitives and can calculate symbolically. And then more often we use numerical differentiation. In other words, we calculate numerically because very often we don't know all the data is complicated, we cannot calculate symbolically using numerical. And both of these are very problematic in high dimensions for complex functions. So, and not being able to have differentiation. This is a technique that in fact combines symbolic and numerical differentiation, and it automatically computes the derivatives of functions. It's a very, very, very powerful technique, and it's the most commonly used technique in scientific machine learning. Scientific machine learning is largely based on this capacity, the capability to do automatic differentiation. So it's good to understand how very quickly about what I don't have time. Okay, so basically, remember, differential programming is based on the concept of gradients. The gradient is a function that tells you in which direction your function is changing, and if you want to go towards a minimum, you should go in the direction in which it changes. And take what's called descent, and then we construct what we call gradient descent algorithms, which are the basic algorithms for solving minimization problems. In machine learning, you know, essentially they got the best brains in the world and had to solve a minimization problem. Google had to solve a very big minimization problem. Google had whatever. So they developed, and it existed already, but they put into practice the use of what's called stochastic trading. So I won't go into the details. It's fascinating, very, very interesting numerical method of stochastic trading. We don't have time to explain what it is. But in fact, it turns out that this is an extremely clever and efficient way to minimize functions that have very high dimensions and that are noisy and are full of local minima and discontinuous terms. Discontinuous and derivatives. These horrible functions we saw before With noise, stochastic gradient does an incredible job of solving it. Okay, so we get to profit. Okay, so basically it can be used. We get to solve many problems. We can calculate gradients of the loss functions. We can solve differential equations. Why can't we calculate the derivatives? Differential program can calculate the derivative of anything. You give it, you want to calculate UDT. You have that as a view. You calculate UDT. You want to calculate d2u dx2. Automatic differentiation with it. You can calculate any derivative. And then you can also perform optimization. And we can solve what's called inverse data set. That's subject of a more advanced course solution of inverse data simulation. We're going to have that. So anyway, if you want to see examples of all these things, in my course that I gave at CSU at Paris State University last year, all studies, I gave the reference at the beginning to get the example. Symbolic differentiation of limits are one way of doing it. Now, numerical differentiation, which we know this, everybody says this is the way to do differentiation. In fact, it's a terrible way of differentiating when you have real data. It doesn't work. There's no way you can differentiate a noisy function in very high dimensions using numerical differentiation. I'm sorry, it doesn't work. So we need what's called automatic differentiation. So I won't go into it, but it's okay, you can read all about automatic differentiation. All I can say to you is that the recent progress has been spectacular, and at the heart, why is machine learning been advancing so quickly? Because it has an ability to obtain high-quality solutions to what are called non-convex optimization problems for functions with billions or even hundreds of billions of parameters, and in the non-convex optimization problem, to solve noisy non-convex optimization. So that's the secret behind the success, really mathematically, of Google and all these other people who are developing all these machine learning, OpenAI. They're all optimizing and using optimization. Okay? So the idea is we can use this incredible opportunity to help us to solve a applied mathematical problem. In particular, a large non-convex optimization. So the reason we didn't make much progress in this until now is we didn't have the tools to solve it. And now the algorithms are available, open source software, benchmarks, and this is thanks to the fact this open source is very good, which is something machine learning community can teach to all of us because it creates a lot of competition. And the competition is good for solving difficult problems. It's like, there's some groups. So that's why I thought this. Okay, so there's a few, I won't go into all the details because based on what's called back operation and autograd, to use it, these you can go. And these tools for automatic differentiation are available in very, very high quality software. They work very well on GPUs. So they can be computed extremely efficiently, extremely quickly. And they're very soft. There's new software, JAX, PyTorch, TensorFlow. All these machine learning packages contain automatic differentiation tools. Okay? And it has the advantage also that it's cheap and easy to compute. That goes into it. And this makes it possible for users to implement gradient-based optimizations for functions with an incredibly large number of parameters. So it's very good. So there's just three things I want to say. This guy, Picardie, is a very well-known researcher. He worked for Tesla. He was responsible for all the AI of Tesla. And recently he joined OpenAI. So he said, gradient descent, he means autograd, automatic differentiation, can write better code than you. I'm sorry. But there's no reason anymore to define differences. He's saying, I'm very sorry, and it's true. Autograd can write better code. And he said, you really should understand backup is the algorithm that's used to calculate the gradients. I'll show you what backup is. Backup is has to do with adjoint method for computing partial differences. of a loss function with respect to the parameters. And he said he's one of the developers of Nakhon. I've been using PyTorch. PyTorch is one of the most important machine learning platforms available, which is used by most of the very important programmers in machine learning in the world. He said, I've been using PyTorch for a few months now, and I've never felt better. I have more energy, my skin is clearer, and my eyesight has improved. In other words, it's very good. It solves all your problems, that's what he's saying, which is, and to some extent, is not exaggerating. It solves problems that until now simply could not solve. Optimization problems. So we want to use that to make our machine learning more scientific. It wasn't developed by that time, okay? But I'll show you that we can use it very efficiently to make machine learning more scientific. So it's based on propagation. So I don't have time, but I think, as a mathematician or as a serious scientist, you should understand the tools that you're using. If you're using the tools as black boxes, at some point somebody's going to ask you why they do this and why they do that. And if you don't understand the tools you're using, you're not going to be able to respond to those questions. Okay. So anyway, I need to go over this a little bit. It's not very complicated mathematics to show you that this is how we're going to proceed. So you can take, to solve any nonlinear, non-convex optimization problem, either for a dynamic system, the XTT equals some f of x and t. So I put some parameters in there. There's always parameters, okay? You'll see that, in fact, very often, in the optimization problem, we want to find the values of theta, which minimize some loss function, which has to do with the system. I'll explain. And we've seen already in machine learning knowledge, you remember, it's just y equals f of x and w. X is the input parameters, the independent variables, y the response of the dependent variables, and w are the weights. It's equivalent to theta, it's equivalent to the parameters in an ODE or PDE. In machine learning, we have weights. With this minimization, in fact, it's min over w. You have to minimize over the weights. And then you say what you're minimizing over. Yeah, so you have L, you can call this function L X, and it depends on the, and you're going to equals this, and you're going to minimize over W. In other words, what you need to minimize over W, you know how to do that. High school. You calculate dl dw. Okay. And then, what's that? It's a gradient. It's rather complicated gradient. It's a gradient of a very noisy, very high dimensional, very non-complex problem. Okay? Because we want to be able to use real stuff now. But it comes down to this. Okay? Then you're going to say f equals 0. In fact, it means we're going to use some kind of gradient algorithm to solve the problem. Okay? This is a necessary condition for the existence. And if we can solve that problem, we can find the values. That gives you an equation in W. Okay. W can be of dimension 10 million. That's the problem. And L is a horrible, non-complex, non-linear function or functional. Anyway, function. So, to find the minimum, you understand we want to find the minimum. This is important because we're going to use this optimization property in order to put the physics. That's why I speak about that. Physics will use this. We're going to put the physics into this framework. As I said, we're going to do multi-objective optimization. I'm going to add another term to my minimization, and the other term is going to be a term that's going to force or require that the solution also satisfies the physics. It's not very complicated to do, I'll show you. But what is physics? Physics is just it's L of U equals. So I can say L of U. I can call it another, I can add a term. I can show that it's positive. I can take the square of L of U, and I'm sure it's always be positive. L of U is just du dt minus d2u dx squared minus f of x equals 0. Just say I have a diffusion equation a heat equation with the right-hand side equals X with initial conditions and boundary conditions. And I just write it in abstract form as L, maybe I'll put L phi for physics. Okay? And this will be LD, D for data. This is the data loss, and this is the physics loss. Okay? There's no reason why I can't express my OE, PE, whatever, as L of U equals 0. U depends on X and T, so U and U X T, okay, whatever. And so I can formulate what's called a multi-objective linearization problem. And then I say, okay, these machine learning people, they have this magic, incredible, very easy way of solving these complicated problems. So I can use that. I can benefit from that. Put my physics inside using this cost function approach, because I know with a cost function I can make an optimization problem. I can use autodiff or autograph as automatic differentiation capacity for these amazing beyond the network of machine learning frameworks. And that's the whole idea. So if I generate a loss function, very often in physics we call the loss function J of x and theta, or L of W, there might be some theta inside, then the best way to solve this optimization problem is to use some gradient descent. So then that propagation, which is part of the sort of differential, is just a way of calculating the derivative of these cost functions with respect to theta, or with respect to W. In other words, we'll find the W's such that this guy reaches some minimal landing level, I reduce my current to something reasonable. So it's really, it looks quite simple in fact. So, alright, this mathematical proof that this is completely what we want to do. So you remember gradient descent, just started. Okay, gradient descent or steepest descent, we start from a starting point and we move in the direction of the gradient until we reach another point, and then we take step size and we go down until we find it. In these type of problems, the optimization space is in fact one coordinate for each weight in the network. Usually in the network, let's say it's a neural network, or it could be a linear regression. Usually we use neural networks. Why? Because solving systems of ODEs or non-ODEs or PEs, it requires much more complex, much more higher order methods. We cannot do it just with a simple regression. A simple regression will never capture the complexity of the relation that's described as some business. So the optimization parameter space is the space of weights, these are the W's. Okay, that's a simple case of linear regression, it's just beta 0, beta 1, beta 2. But I'll show you very quickly afterwards. In neural networks, it becomes much more complex. And then, very high dimensional, hard to visualize, but we usually want to compute the loss gradient, so we can have the gradient with respect to W of L, which is just the LDW, and the gradient of theta with respect to L. Or in general, I can just say gradient with respect to Z, and then Z equals W, Z equals theta. So this is a very, very general approach which can be used to minimize, solve a function either with a data loss or with a physics loss. I just have to express it in this form. As a loss, I think which equals 0, and I look for the parameter values which will realize the minimum, what's called the argument that fixes the minimum. Okay? I don't have time to work this up. So anyway, all of this uses the chain rule. It's like, so if you see a glass, you can say, why should I learn the chain rule? This is why you should learn the chain rule. It's in fact, if you understand the chain rule, then you can understand how machine learning works. It's great. I'm showing you secrets. It's just the chain rule. Chain rule and then optimization. Looking for F. You're looking for the mapping, but the mapping is the mapping that minimizes this thing. Okay, so, if you want to go that's some very simple stuff with chain rules. Everybody knows how the chain rule works. If you want to differentiate function of F as a function of T, you take the derivative with respect to x, and then you take the derivative with x with respect to t. And that can be generalized to many. So in general, I'll just show you some examples. So I can show you how I'll program an automatic differentiation for you. Very simple to program, but afterwards for more complicated functions, it's better to use the routines. In fact, it's not complex. That's the secret of success of machine learning. In fact, they're using very, very simple things done extremely efficiently, and that's why it works. Otherwise, it would never work. So you must be, people, it's quite easy to understand, and I think it's important to understand. If we understand, of course, then we can use it for other things, and that's the idea. So let me take a simple problem: f(x) y z equals x plus y plus z. What you do is you decompose it into simple differential elements. You say qx equals x plus y, and then f equals qz, and then you can calculate easily the f dq, and then the f dz. Okay? These are very easy to do. And then I can calculate the q dx and the q dy, and this way I differentiate by the chain rule f with respect to x, y, and z. So you see, you can break this is what they do. They break it down into elementary blocks, and then all these elementary processes is put into what's called a graph and a computation. And you can program this very easy. In fact, this little piece of Python is doing the chain rule very easy. No symbolically, no finite difference, okay? Which means it's not sensitive, means it can differentiate anything. Because I'm using a mixture of symbolic and numeric. These are exact, it's precise to machine precision. We obtain the gradient, which sometimes called sensitivity. So I've got the f dx, the f dy, I have all the partial derivatives. If I have the partial derivatives, in fact I have this. So anyway, it's got the graphs. You can have a look and see how it's done. It's very easy, and the automatic differentiation is just an implementation of what's called a forward pass and a backward pass. So you see you go in one direction, and you compute the values with the outputs, and then the backprop, that's why it's called backprop, calculates. You calculate f, and then you go backwards and you calculate the f dq, and then the q dx, the q dy, and the f dz, and eventually you see you get the numbers. In fact, you do it numerically, but you're using known derivatives of primitive functions. So in fact, anything can be differentiated. As long as you decompose your software, your code into primitive functions, or one knows how to do it, then one knows the derivatives and so on. Okay, so you can use it for solving on the equation of sensitivity analysis and circular propagation of machine learning. This is very, very useful once you can do differentiate it quickly, efficiently, and accurately. And then, there's some examples. If you look, you can have a look at some simple examples with that now. So I can show you if you do it by calculus, it becomes very messy very quickly. I took this function, sigma times wx plus b minus t. This is wonderful moment when you're on that. Just to show you that if you do it by hand, you get the LDW and the LDB, because you want to find the coefficients W and B to minimize this. So in addition to the W, there's also another coefficient that's called D, that's called the bias. This is damage of neural networks. It becomes very messy. Whereas if you decompose it, like we did before, one can create what's called a computational graph, and then it's very easy to calculate numerically. This partial derivative of L with respect to each one of its parameters. You have what's called direct forward propagation, the compute the loss, and then a backward propagation. So in two passes of the function, we calculate the derivative of L with respect to each one of xw. Alright, so this is what's called backpropagation, and it's nothing else but the chain rule, and it gives you the derivative of L with respect to w. And if you minimize that, then you can find the coefficients w, which creates, or the coefficients beta, which create the y-hat, which minimizes the L2 error, you solve your problem. So, machine learning is that. The rest, as I said, the rest is just just details. It's just technical details. Of course, the devil is in the details. Of course, it's the details that take all the time. But conceptually, everything can be resumed by this time. Okay, so the idea is, okay, I'm not going to go into it, but it's quite easy to implement, and you can look at the function inside Python and inside TensorFlow and other things is called autograd, and you can use autograd to do this. Okay. So, now, going back, so I said we need to combine machine learning with science, and usually the combination is done based on neural networks. So neural network is, we have spoken about, for example, neural network is one of the most efficient, let's say, one of the most powerful methods of finding f when we want to go f. Now, why are the neural networks the most powerful way of finding this mapping f between x and y? Remember, we're just looking for f. Remember, I always said looking for f. We're just looking for this f that's going to be a mapping from input data to output data. In other words, we just need data. To find f, you just need data, right? You don't need any theory, okay? Anyway, so neural networks are exceptionally good at doing this. We have open source software, and neural networks possess what is called universal approximation property. This is a theorem in approximation theory that was proved at the end of the 80s, 1989, 1990. Well, it's quite about 35 years ago, which shows mathematically, rigorously proved that a neural network can approximate a function of arbitrary complexity with arbitrary precision. This is amazing. It's like the super approximator. You don't need anything else but a neural network to solve this problem. So what is a neural network? In fact, it's very, very simple. You can look at my course here. It's just a composition. Yeah, I take a neural network with three neurons. Okay? So it's just a composition of scalar product between the weight and the x plus a constant term. So this is just a linear polynomial, wx plus b. It's like ax plus b. It's like b to 0. So it's just as if I just take this part. Okay. And I use that as the basic building block of a neural network. It seems very simple, it's very stupid in a way, but in fact, one can prove. Okay, then I apply the function sigma, and sigma is a nonlinear function. So the sigma introduces nonlinearity, and then I do a composition. I take sigma 1 of that, and then I take sigma 2 of everything. And then I can take W4, sigma 3 of all of that, and I can add a B4, etc. So you can iterate this in terms of composition of functions, and in this way you construct an arbitrarily complex function which has certain properties. So the whole idea of training, everything we've been doing is given observations y, or some island function f, find the values of w, and minimize the loss function that expresses the mismatch or the error between the predictions. You can call it nn of x now. Neural network is that, and the corresponding y. So nn of x, y hat. Y hat in my case, the neural network equals nn of x. Okay? I just need to know x, and I get an approximation of y, and so you see neural networks is the same as this, it's the same as this, just going one step there. Okay, a neural network is nothing else but a function approximator. It's just a good, so if you like approximation theory, you can, where's the, okay, so. It also avoids the first dimension. It has other properties on the neural network, that's why it works. And here are the two theories. If you want to go, the proofs are not very simple, they're quite long, but you can find them in CIMPA 89 and 90, 89 and 90. So the two theorems that said that if sigma is any continuous sigmoidal function, then finite sums, are dense in the space of continuous functions. That's an approximation property universe. And there's another very nice theorem, I think this which came out 10 years later, which says that suppose that sigma are not polynomial, they're nonlinear, then the space of neural networks have one hidden layer only. I'll show you the program neural network. This space is dense in the space of continuous functions of order n, of any order. So you can get arbitrary smoothness of any power just by using these guys that I showed you. Just by using these guys. These are enough to give you dense approximator. Sums of these are dense in the space of continuum functions, and the space of continuum functions of any degree of continuity. This is amazing. This is crazy. It's like, oh. So neural networks just implement this. The guys who developed neural networks, they knew well neural networks were started before they really got their theoretical basis. They were started in the 60s or the 70s. They were called multi-layer perceptrons. Okay, there's another history. So neural network is just this. You take your inputs, just say I've got x1, x2, x3, x4, just say I've got, temperature, pressure, concentration, humidity. I want to predict the rainfall, I don't know. And you put it into a neural network, and I'll show you the math behind that. And out comes, well, that's y hat. It should be y hat. It's an approximation to y. The neural network is just, and the neural network is the sum of composition of sigma, which is an activation function applied to a scalar product w I x I plus v. That's just to give a constant term to approximation. So that gives you, that's all it is. I'll show you a more complex one. So in scientific machine learning, neural networks and machine learning are used as the basis to solve problems. Okay. How are we going to do this? Usually in CSE, computational science engineering, we have a system that describes our physics, which is written as PDEs or DEs, these are partial differential equations, and we're interested in how they evolve and how they change. Okay. So the solution of these differential equations by machine learning is an interesting subject. And we can see that machine learning can be used for many other things as well, relative physics. So recall the question of balance. So remember, using data only and no science, you're going to get machine learning models. If you use science only and no data, you're going to use computational science and engineering. If you use both, you're going to get some kind of scientific machine learning, and that's the idea. So there are different approaches for scientific machine learning. We have what's called architecture-based, loss function-based, and hybrid approaches. I'm going to show you just the loss function, because we don't have time for this, but there are many different ways of combining, and here I have some of the examples. So there's a whole list of, so as I said, this is it's not very old now. It's like 5-6 years ago. There's a lot of people and a lot of money being spent on research into this thing. So there's a lot of stuff out there. We don't have time to touch on one aspect, which is the loss function-based approach. But there are other approaches that want to set still. It's the one that seems to be the most easy to. Okay, so very quickly we speak about this. That's not exactly the point, but because often, in fact, the big challenge today in computation, CSE, computational science engineering, it's not how to solve the PD, how to solve the OP. That's what's called the direct problem. I give you all the input parameters, I give you X, I give you T, I give you all the coefficients of the PDE or the OT, and I ask you to find U, the solution. That's what's called solving the direct problem. That today, basically, we know how to solve anything and everything. You use finite difference, you find element, you use finite properties. That you can solve Nakhon, you can solve Maxwell, you can solve SIR. We have methods for solving direct problems. That is something that's been solved up to the 1970s, 1980s. That's it. That problem is more or less finished now. There are a few challenges because we want to solve more precise, less time problem. You can work a lot on the solve, but you don't have to solve direct problems. I give you the model parameters, and you know the physical partial or ordinary differential equation, you can predict the observations. You can create observations. The challenging problem now is that because in this physical PDE, for example, there are parameters. And the big problem is not the fact that we don't know how to solve the direct problem. The big problem is that we solve the direct problem, we don't know exactly what the parameter values are. That's the problem with coding. There were many super predictions of what would happen, and they were very, very, very far from the reality. Why? Because the equations were good. The equations, as I say, hundreds of years, very great scientists observing nature, modeling, we know how to model. It's not that the equations were bad, it's that the coefficients, okay, there might have been missing terms in the equation. Supposing that all the terms, there are enough terms in the equation. The problem is that the coefficients, the gamma, the alpha, the beta, whatever what you call them, sigma in SR, the coefficients were bad. And so, the challenging problem today in computational science is the inverse problem. It says, can I use the observations in order to improve my equation? Okay, which means, can I use the observations in order to estimate the parameters of the equation? You understand the ODE? I'm not going to write it. An ODE has derivatives and it has coefficients. The coefficient could be linear or not linear, they can be independent type of whatever, but they have coefficients. Alphas, betas, gammas in front of the derivatives. And the big problem is if the values of the parameters are bad, your prediction of the evolution of COVID or whatever are going to be bad. You've got the right derivatives, but you've got the wrong values for the coefficients in your equation. So, one of the major problems today in computational science engineering is to solve the inverse problem. It says, suppose I had observations, but you see, we're coming close to this now, okay? Because I have observations. These guys, they know how to solve problems. They know how to find parameters, okay, for machine learning using data. So yeah, the inverse problem that we want to solve in computational science is given the observations, I don't say how they come, and knowing the physical law, can I estimate the parameters? You see, I'm doing the other way. Here, I'm given the parameters, I find the observations. Yeah, that's direct. Finite difference, discrete feather, whatever you want. It goes this way. For me, that's trivial. For me, that's not an interesting problem. The interesting problem is this one. I give you observations, and I want you to find the parameters. And then, if you put the good parameters, you put these parameters back in here, and obviously your observations are going to be. That's inverse problem. So, inverse problems. And this is exactly the same. In fact, this is an inverse problem. I give you the observations. Machine learning is solving what? It's solving the inverse problem. We are interested in solving inverse problems. And you start to understand that it's quite possible that machine learning methods can be used to solve our problems. That's problems that they are difficult to solve. There's lots of problems we solve. I'm not saying you stop solving problems, you see. Everything that you've learned so far. I don't say delete. Okay, I say keep that when you have a problem which you cannot solve satisfactorily. These guys know how to do it. They're doing it. I don't say that it's easy that they're doing it. They do it extremely, extremely efficiently when it works. Okay, to make it work. Okay, so that's why it's important to know the difference between ordered inverse problems and to realize that an inverse problem is nothing else but a machine. The same formulation as the machine learning problem. So you see, in fact, we're very close to machine learning people. Machine learning people are not mathematicians solving inverse problems. But now, as mathematicians say, oh, wait a minute, these guys, okay, as I said, good salaries, good working conditions, best PhD students in the world. Okay, they did an excellent job of solving inverse problems. It's clear, and they make a great open source software. In addition, they're not keeping results and so on. It's obvious that for us, scientists, we should try and see how to use their methods to help solve our problems. So that's the whole idea of scientific machine learning. Okay, it's very easy to say. It sounds magic. Here's machine learning. But of course, it's not as easy as it sounds. In principle, it is very, very simple. The principles are very easy. And what I say, what is important is not be able to solve the problem, but at least to understand how these problems are solved. And if we understand, that's what it gives you interpretability. And it gives you some way of analyzing what's happening. You know what you're doing. And don't like when anybody or students or whatever use methods and they don't know what's inside. That is extremely, extremely dangerous. When you use somebody else's method, his method works for his problem or her problem, but there's no guarantee that it's going to work for your problem. Your problem is always different. Otherwise, if your problem is the same as the other person's problem, well, then there's no reason to solve it. It's solved already. So obviously your problem has something new and something different. And if you want to understand, want to use somebody else's theory, you must understand the theory. It's the same in mathematics, the same in physics. The major challenge today, extremely high computational costs, etc. Okay. Alright, so forward problems are easy. Inverse problems are terrible. Okay. Many challenges. I won't go into them, but you can read about this. Mathematically, these problems are ill-posed. There's not an existence. There's not uniqueness. There can be high sensitivity to initial conditions. Okay, these are very, very inverse problems. Yeah, it's easy for me to draw the arrows here, right? In fact, the mathematical formulation of this problem yields what's called an ill-posed problem. Ill-posed problems are difficult, and that's why also numerical physics really to solve this. Yeah. So that's why we tempted to look at this, because they are exactly solving the type of inverse problem, which for us theoretically and even algorithmically in terms of computational calculus science is a very, very big challenge. And these guys, we've been doing it. Not for long, but they've been doing it. It seems to work. So that's the motivator. So let's go. So here, as I said, there are many, many ways of combining machine learning and science and computing. I don't have time to do them all. I put it in gray. There's a lot of, and I have to go up to 170. There's a lot of stuff that's gray. If you want to do equation discovery, these methods, I said you can find unknown parameters. Machine learning. You can even find an unknown equation. It can discover the equation. You give it data, and it will discover the equation. Okay. You have to give it something. So just to say, machine learning, it can do amazing things. I don't say that's easy, but okay, so equation discovery, we don't have time. Next time. Okay, so let's go. This is equation discovery using machine learning. I'll give you some references. Something at the University of Washington. They are what are called architecture-based methods. So a neural network has an architecture. We'll look at the neural networks because I'll be showing you the loss function-based. So one can use architecture-based methods also to include physics inside. However, think about that again. There's a whole thing that's for surrogate modeling. Other than that, this is also very important. You can go to the surrogate modeling. It's used in many ways. I like surrogate modeling. Okay. No time today. We have time on that. Surrogate modeling is something that can be used in any case, which is useful. Anyway, I've been using it a lot. I've been working on new generation of lithium batteries for electric vehicles. So I work on research to developing, analyzing new batteries for EVs. And we're using a lot of surrogate modeling for that. So if you want to speak about those. There's what's called physics constrained learning, which is not very far from what we're going to do, but we're going to we're going to look at physics inspired learning. These are names that have been given that okay, we can look at that mathematical formulation. They all related somehow or another. They're not very far different, but there are all ways, different ways of including physics, of combining physics or blending physics and machine. Now we have physics inspired. So the idea, put the PE into the machine learning. Okay. How are we going to do it? We're going to use the cost function. As I said, we're going to add. This is LD. I'm going to add L5. Okay, I'm going to add a second term. This term will just be another cost function term, something like this. This is something like this. But I'm going to put the PD in it. How am I going to put the PD? Well, the PD, I showed you, automatic differentiation. Automatic auto can differentiate anything. And it does it with far greater precision, does it with machine precision, and it can deal with noisy data. Okay, so you see, I've got all the pieces now. Now we're going to make the cake. We have all the ingredients to make the cake. So these we introduced this okay. There's a lot of this is quite recent. The first papers that came out in 2018, these papers already have a lot of citations later on. The original papers are around 5,000 citations. I don't know if you Google Scholar, the number of citations. It's 5,000 citations for one paper is a lot. So these papers, the original papers by a group of George Pathom. George Pathom is a professor at Brown University in the United States on the East Coast, just north of New York, close to Boston, between Boston and New York. And his team around him developed these approaches. So anyway, one can explain, it's called soft constraints. We can use approximation optimization theory to understand the spectrum. So I won't go into it, but we know that our problem is that the loss landscape is very difficult. So there are different ways now. Okay, this method is running into a lot of problems. It works in some cases it doesn't, but there's a lot of research being done in order to improve that. So I won't get into those. What I want to look at is first of all how we solve the PDE with the neural network. We can actually use the neural network to solve the PDE. And then we can use the neural network also to estimate its parameters, because for the neural network there's no extra work to estimate the parameters. So the idea is to use the network to approximate the solution, and while at the same time satisfying any other physical constraints. So what we'll do for scalar ODE, for example, the neural network will have one input which is the dependent variable, and one output which is the dependent variable. Okay? It's the XDT, that the input will be t, and the output will be x. Okay? The neural network will be trained to minimize a loss function that includes both the error at the data points, that's my data error. So we need to have some data also. This supposes, well, okay, we cannot solve a PDE using neural networks if we don't have data. But the idea is to say, oh, we have a lot of data. We measure it all very often. We don't have measurements of everything, but we can generate measurements. How can we generate? We solve the direct problem. We know that we have to solve it. We can generate some data. We can put some noise and say, oh, and that data looks more or less like what's happening in the real world. So I can use that data to train a neural network. And once I have the neural, I have the F. Once I have the F, I don't need to solve the problem anymore. The neural network will solve the problem. And the F is just a function. F is just, in this case, it's just beta 0, beta 1, beta 2. So it's just a collection of, it's a bunch of coefficients. So you want to use your neural network solution F to solve, to have an estimation of y. Just give me x1, x2, and immediately, this is instantaneous. This is why, this is called the inference stage. This is why neural networks can solve, once they have been trained, can solve an incredibly complex problem in milliseconds. It's really a question of milliseconds. You have to solve a very complex Navier-Stokes equation, a large number, using finite elements or finite volumes. It can take you 3 or 4 or 5 days in a turbulent regime to solve a Navier-Stokes equation. Neural network is learned the F. Now it's just learned, it has a vector of coefficients. In the case of a neural network, it's the same thing, except for you sort of it. And all it has to do is to evaluate this very complicated polynomial evaluation. For a computer, these guys, they don't care. You ask them to evaluate polynomials, they'll do a polynomial of more than 10 million. You can few couple of million as long as your vector fits inside it. It does it instantaneously. Do you understand why this is interesting for us? Because it enables us to solve very, very complicated problems in very, very short time. And if we can solve it in short time, then we can make all kinds of studies. Very often we want to know what happens if the infection rate gets big, if we make the quarantine period longer. We just have to put these new values inside the equation and out will come the solution. Okay? If it's just changing the independent variables. I told you that x1 can be the temperature, x2 can be the pressure. You can vary things and you can get instantaneously the solution from it. Okay, so that's the idea. And as I said, it's the sum of two errors. Data error and differential equation. So how do we do it? I'll show you and we can see. Then solve direct inverse problems. Okay, that's what I said before. I want to show you. Okay, this I'm just reformulating parts of this is just to put it in the framework of optimization theory. And here you see what I'm doing is I'm minimizing a sum of two cost functions, and these cost functions represent the misfit here. I call it U0, the notation. This is LT, and LUB can represent the misfit. That's going to be the loss function, which shows the error on my neural network of my y-hat with respect to the initial and bounding conditions. And then I have F. What is F? F is just my differential equation, or my system differential equation. So you see I have three terms. I've separated here into three terms. 1, 2, 3, where I put the data loss, the bounding condition, initial condition loss, and the PDE loss. This is the physics. Physics coming into the neural network. When you use a neural network to solve this problem, it's going to minimize that there's data loss, there's PDE loss, that's the data loss, and there's bounding condition loss. So all of my physics is now inside my loss function. If you say I put it into the neural network, well, not exactly, but it's correct. So, what does it look like? Warnings, okay. Sounds very easy. It's very easy for me to say, yeah, so, we just do it. But, okay. There are problems. Even in paradise, we say there are problems. And this is not paradise. So there are problems. I won't make sure that we obviously things are not as it looks. Okay. There's some way. Step by step, you go through the steps. You're going to get there. Don't worry. First step, you have to define your neural network architecture. Okay. Yes, have the input layer, output layer, whatever. Hidden layers. Okay. The number of neurons in each layer. You have to decide. That depends on the complexity of your problem. Usually, you want to try something simple. Let's say we try something complicated. You simplify to the point where you have acceptable errors. It's the same thing. Neural network, by making it more complicated, afterwards, you remember my curve, you're increasing the complexity. You're going out to a point where your loss of your training error is small, you're increasing the complexity. So neural network is really complex, like adding more neurons and more layers, more complex. You're going out onto the right. So be careful, you're going to have problems with your test error code. Because you're using neural networks, that's why I started today with model validation. You're still going to use model validation, which is good. That's good practice. These are things that in computational science you will never worry about. You never did model validation like that because we have converters. We have converters result for an equation. It's big O of H, and if it's a PDE, and if you have a consistent and a stable scheme for your finite difference, then you know that you have big O of H plus big O of delta T, and you know. That was the easy life, but in the real life, we have data, we're using data, and so we must use now because the data has lots of random variations. Why? Because we want to deal with reality. Otherwise, we're just doing average and saying functional variable. So, one can use, now that we're using neural networks, we will also use all the validation, cross validation, etc., training sets, validation set, test set. This is very, very good scientific practice. It makes the science trustworthy again. Okay? You can say, all right, but that I don't expect you to understand because you're the person at the health administration. who asked me to make a study about DNA, and this is what it proposes. You don't expect them to understand every line of your code and what's in your method, but at least you can say, I've used all the validation procedures, and in terms of the best practice that is known in the world today, this can be justified. I've tested it against different combinations, different validation sets, and this is the average performance of the method. Sometimes it can perform better, sometimes worse, but I tested it in a very formal, a very good way. And then, okay, neural network architecture, you have to collect a data set of known solutions, so you need data. Then you need to define the loss function. Okay, I've started the loss function. And then train it. Okay. And then, once it's been trained, you validate, and then you can use it to approximate the solution to different situations. So I'll show you, okay, it's a repetition. So you have the global loss function is the data has a data term, it has a boundary condition term, and it has a differential equation term. Nobody says, if you're minimizing L, you can put L1 plus L2 plus L3. It's still L1. Those they positive functions. You just square them and they become positive functions. Nobody says that L has to just be equal to one term. You can put as many terms as you want. Afterwards, the question. Balance between the terms, in fact, there should be an alpha 1, alpha 2, alpha 3 here, because we have to make sure that all three terms are participating in the minimization. Oh, that's multi-objective optimization, which is known to be, as by itself, is something that's not so easy. That's why I say it looks very simple, but in reality, there are maybe little steps, lots of details. But anyway, let me show you. This is what it looks like. Okay? I told you it was simple. Okay? So, you've got X and T coming in. You've got your neural network. Yeah? It's giving U hat. I take U hat, and I use autograph, and it gives me any derivative I want. All the derivatives, first order, second order, partial derivatives, ordinary derivatives. Trivial. These guys have solved this. They said, I'm sorry, but autograph will write better code than you. You cannot do better. You cannot even do as well using finite differences, using finite. You cannot just forget it. Use autograph. It's extremely, extremely good. So it means I can calculate all my derivatives. So I've got U, this is my data. I can calculate a data-driven loss. I've got my PE. I can calculate the PE is just say it's UDT minus dudx plus dv. I just put the PE in here. That's my term F or L phi equal to 0. And then I add the two. I have a loss function. And then minimize. I showed you. That's why I started with optimization. In the end, you have to be able to solve an optimization problem. But as I said, these guys, they are found. The reason that they are what they are today is because they know how to solve optimization problems. And so they use stochastic gradient and automatic differentiation. Automatic differentiation they use a lot also because they can do sensitivity steps. So you see, that's all. Yeah, I can put any differential equation, any system of differential equations, linear, nonlinear, I can put a PDE, I can put an integral equation, I can put a stochastic differential, I can put anything inside here. Well, stochastic, not so easy because I cannot have derivatives. Anything equation that has derivatives, I can even put something that doesn't have derivatives. I can have an algebraic equation, I can put it in here as well. Okay? Just an extra term in my cost function, and then give it to the minimizer. And I said the minimizer, the stochastic gradient is, well, okay, it's not as easy. Sometimes one uses stochastic gradient, and then one uses a classical method afterwards. One does what's called transfer optimization or phase optimization. So you can still use, what's used a lot is LDFGS or VFGS, that's Freud. Optimization is a very, very classical optimization routine as well. Quasi-Newton optimization routine. These are still used. So what doesn't use today physics problems is turned out just using stochastic gradient sometimes isn't enough. One uses stochastic gradient for 1,000 iterations, and then one does 500. Stochastic gradient is a first order optimization routine. Convergence is first order. And if you want something that's second order that the convergence is quadratic, then one has to use some kind of quasi-Newton method. And the quasi-Newton method is sometimes used for these type of problems. After using the stochastic gradient, one does a couple of hundred iterations using what's called LBFGS, which is it's a variant of the BFGS, the Breuer-Goldberg-Shannon quasi-Newton optimization routine. These are classical optimization routines, BFGS, which we study when we do classical optimization in computational science. So it doesn't mean you can throw away your computational science. They have, fortunately, computational science is still very good. So that's good. That's good. Okay. And then, let's see the neural network. The neural network is complicated, depends on its architecture. I have some pictures. And then I've described this and that. It's good to have a nice mathematical formulation of the problem. And one can formulate the neural network problem in terms of mathematics because we know the functional form of the neural network. I showed you the theorems, the approximation properties. These theorems are mathematical theorems. The neural network, of course, has a mathematical expression. So you can express it exactly. And so you can write down, if you're doing a paper or doing a thesis or doing research, you have a nice mathematical expression for it. There's no reason not to do it. And then, as you see, I told you it's a composition of functions. Neural network is a function of x, that's the input, and theta. Theta is all the ways to the coefficient, and it can be written as a composition of n functions of n. And these functions depend on the input, n is the output, is the y hat, n is the number of layers. Each fi, this is all neural network, all of the simple or fully connected neural networks, or the basic multi-layer perceptrons have neurons. This is the neuron, which is an approximation of the function of the neurons in the brain. That is, the only approximation is the fact that the sigma is what's called a threshold function. So there's a threshold. The brain works for thresholds. The nervous system works for thresholds. So threshold functions or sigmoid functions or functions of this type. They can be like that. They can be like this. There are many. These are hyperbolic tangents or sigmoids, or this is called rectified. You can see below 0, less than 0, nothing happens. When you go through 0, suddenly it goes from 0 to 1. These functions. So neural networks use these sigmoid type functions, and these sigmoid type functions are an approximation of how the neurons in our brain and in all of our work in fact function. So that's the reason why it's called a neural network or artificial intelligence, because it's based very loosely on the chemical behavior of using thresholds of how the chemistry of the nervous system works. Anyway, so these functions are like that, and theta is just a connection of W and V, which always equals a linear term, a linear coefficient of a linear term, and you add a constant term. You say, it's linear, but don't forget, it's a composition, so it becomes composition, and sigma is a nonlinear function. Sigma is a sigmoid type function. It can be a hyperbolic tangent, or it can be a sigmoid function, or it can be what's called rectified linear unit, which is some approximation of the threshold. So you see the nonlinearity is introduced in that way. This gives us the universal approximation property, and that's why it's a good approximator. And then you have to find the weights. And then it looks like, it looks like that. In reality, it looks like this. You have the input there, you have the output there. Okay, so everything you're putting into the system, everything you measure, it can be a single point, it can be a vector. This is a vector system. This is S-I-R, for example. And inside you have layers. Each layer has a neuron. Each neuron is one of the sigmoid functions multiplied by WIXI. So you have 4 x's. X1, X2, X3, X4. Temperature, pressure, humidity, So I'm going to have W1 x1, W2 x2, W3 x3, W4 x4 plus a constant term. I'm going to apply that conversion function, and it's going to give me the output of 1 neuron. And you see that the composition of the function becomes very rapidly very complex. And it's because of that you obtain a universal approximation property. Because in fact, it's a very, very complicated function. You can ask to look at it. If you look at it, you won't understand it. It becomes very good. In the end, this is you can count the number of parameters, and it's the number of lines plus the number of neurons. You've got 12 times 4 times 20, 240. You've got about 1,000 parameters just in this neural network. Okay, so we want to, and you can write for that mathematically, and then after it becomes a question of linear algebra factor to complicate it. So anyway, okay, this is the final formulation again, but I'm repeating myself. So you have the differential operator, you have a boundary operator which captures the boundary conditions, and then you have this approximation thanks to the neural network. And what you notice, one of the major problems in computational science is that we need a mesh. You need to discretize the domain. Here you don't need discretization. It's what's called mesh-free methods. And that is a big relief. I don't need a mesh. Because meshing, in a simple 1D problem, in ODEs, meshing is not a problem. When you start to have PDEs in 2 dimensions, you want to do 3-dimensional problems, you want to capture some spatial dispersion, you want some building, some things, some disturbances. Meshing is one of the major problems. It creates a lot of problems in terms of geometry and in terms of stability. In other words, if your mesh is not very, very well structured, the terms that you obtain in the matrix that you finally use when you use your finite elements, you obtain some kind of matrix linear system. The linear system becomes very ill-conditioned. So meshing is a huge problem. And here we have mesh. In addition, we have global optimization of non-convex, non-linear cross functions. So we have two things that give it a lot of advantages. Okay, so anyway, this is just another formulation. I don't know why I'm repeating myself. And then, okay, well, why did I put this? Oh, yeah, sure. Because you see here I added another term. I called it Li. Because that's the inverse problem term. What's the inverse problem term? I said we could also ask the neural network is our slave. It's going to do whatever we ask it to give or her to do, right? So we essentially not only do I want you to solve the equation, minimize the PDE loss, minimize the boundary loss, minimize the data loss, but I want you to minimize the parameter identification loss, which means, let's say I don't have good values for my parameters in my PDE or in my ODE in my SR. I just say to Mr. Neural Network, Mrs. Neural Network, don't forget that I also want to put into W the unknown values of my parameters. You just got a piece of copper, it's not going to listen to you adding three more unknowns to my optimization problem. That's nothing to you. He's already optimizing. You saw the neural network, thousands and thousands and thousands of W's. You're adding 3 more. So you have 3 coefficients you want to estimate. He does it almost for free. He or she. I don't know if it's a he or she. It. So you just add another term. That's it. Okay? And that represents the loss of your coefficients. Anyway, so solving the inverse problem requires only the addition of a single term to the loss function and nothing more. The rest is then it's going to do its optimization, stochastic gradient, validation, training, then just turn the machine, take this turn. Okay, so that's why. Okay, there's one other thing that's important. So people coming to me and say, yeah, I'm using that, but then if I present a paper, what can I say in terms of error analysis? So it turns out it's a very bright people. In Switzerland, they've been working on the problem of trying to get at least some type of error analysis for the this physics-inspired neural network. So it turns out that one can formulate, which is what we need as scientific mathematicians, applied mathematicians. We like to have that error analysis. So one can decompose the errors. There's a couple of papers here that I recommend if you want to read. They were in archive in 2023. It's possible now they published. Yeah, they wanted to be published in 2023, and subsequently there have been a few more papers by Mishra and Inara, the two researchers at ETH Zurich, which is a very good university in Zurich in Switzerland. They have started, they said that you can bound the error via some of the three errors, which is called the optimization error, generalization error, and approximation error. So there is some, for people who want to write, who want to justify in your paper or in your thesis or whatever, the fact that you use this neural network to solve a physics problem. One can invoke the theory of Mishra and Molinaro to give at least an outline of an error analysis, convergence analysis problem. So it does exist. It's good to know. And then, okay, I've gone into more detail. For people who want more detail, you can go here and find more detail on each of the terms. Exactly, much more detail of how they define the last term of the PDE, the last term of the boundary condition, and then how to choose the place. So, okay, as I said, we use stochastic gradient to do that, and then automatic differentiation. Okay, and this is output. So, I'll show you one example. Has many advantages. You can solve any type of ODE, any type of PDE. It can have very complex geometry, very nonlinear behavior. Mesh tree can be trained with very accurate. It can be trained even with very limited data, and what's more important, with noisy data. You can use noisy data to train. I told you, these guys have been for a long time, and now so their methods, the machine learning methods, are how to train with noisy data. They're relatively easy to implement. And when they work, they provide impressive speed ups. In other words, you solve your equation using free Verna, a complicated PDE, it will take 1 hour. These guys can get 3 to 4 orders of magnitude speed up. Why? If you go 10,000 times faster, why? Because in the end, you just evaluate the polynomial. Okay. Once you've solved the optimization problem, the train can take a long time. But once you've trained and you have the coefficients, it means you just have to evaluate some complicated polynomial. Polynomial evaluation for these little machines, trivial milliseconds, really milliseconds. So you get this incredible speed. But of course, life is not. We're not in paradise. So of course there are problems, and this is a few. But these problems, there's a lot of problems. But it's a very promising way. I don't say that it's the only way to solve PDEs and to solve different problems, but it should be considered today because we have the tools. We should consider using these approaches and to see if you can make them work, and if they work, these powerful tools can be used to solve a wide variety of problems, but they also have some severe limitations. I just have one more example. Okay, there may be many problems and there's remedies. PCs, okay, let's speak about that. Let me see, but I have just one example. But you could do it, as I said. Okay, let me show you this one very quickly. I take a classical initial boundary value problem. There's a very classical PDE for the diffusion equation. The diffusion equation is used in many contexts for pollution or propagation of epidemics in space and time. So you observe it in time, you have a derivative in space, and you have the diffusion coefficient, which can also be a function of space. So the lambda is the diffusion coefficient. Or in general, it's a tensor with elements. U can be a vector. Remember the direct problem. I give you lambda, and you find U. The inverse problem, give it, you compute lambda. So you can put all of this. Okay, and I have not about conditions. Okay, derivative boundary conditions, not boundary conditions, and I have initial conditions. This is the full-blown initial boundary problem with a PDE. Classically, I can solve it. The direct problem is quite relatively easy. This problem is very difficult to solve. Put it into bin, no problem. X and T come in, U hat comes out, auto diff, auto grad, calculates the derivatives. You just need ddt and d2 dx2. It goes into the initial condition. It goes into ddn to calculate. Sorry, this is the Dirichlet condition. This is the Nakhon condition. The loss has a contribution from the equation, a contribution from the Nakhon condition, a contribution from the Dirichlet condition. Minimize and outcomes finite. So you see, the method is the same. You can give me any equation you want, anything. Put anything in there. I've got all the tools I need to solve any problem. So that's not what I did. Use AD to compute the derivatives, minimize the method with the method plus function. And that's it. Okay, how many more goes? There's another 30 or 40 slides here. We speak about operator there. So, okay, now we've learned the solution of the PDE or the ODE. In fact, you could even learn the operator and not the solution anyway, because we don't have time for that. As I said, do it next time. So, then there's combinations of operator value. Okay, it goes on and on and on. And the last thing is GPT. Okay, so I showed you already. Numerical weather prediction is being done by generative pre-trained explorers. Okay, they fill in the gaps using Nakhon chains. At the moment, there's some very, very interesting work being done in numerical weather prediction and climatology. I showed you that they're starting to look at healthcare, make diagnostics from multimodal data. AlphaFold, which is not exactly GPT, but similar, it's reinforced learning. And AlphaFold is being used for drug design. Drug design is a very, very big challenge. And question 4, where are we going? That's the question. We don't really know, right? So we must be careful. Okay, so a lot of applications, and I had a long list of bibliography and a lot of review papers. So if you want to go further, these review papers are excellent. So I've got 3 pages of review pages I really recommend to get more details about everything that I've said. You can get, of course, in these slides are some details I have on my website, on my GitHub, I have some examples, but in these papers you have all the details. Okay, thank you very much.